We propose a new framework for Bayesian Model Predictive Control, SVMPC, for optimizing multimodal control policies. We formulate model predictive control as variational inference over a sequence of decision parameters. Given a family of policies in a dynamics model, these parameters define distributions over predicted state and control trajectories, along with resulting costs. We can then minimize the KL divergence between the proposal distribution and the target posterior over the parameters given trajectory costs. The resulting optimized distribution is then used to generate parameter sequences for the next MPC iteration. In our approach, we employ Stein variational gradient descent to optimize the variational objective. Here, the posterior is approximated using a set of particles over the parameter space. Functional gradient descent is performed iteratively to smoothly update the proposal distribution. The nonparametric representation is flexible and can readily capture complex multimodal posterior distributions. Building on this idea, we introduce Stein Variational Model Predictive Control, or SVMPC, where each particle represents a sequence of parameters. These may parameterize a policy distribution, like in MPC, or directly represent sequences of control actions, such as in the case of trajectory optimization. Scaling to such high-dimensional regimes is made possible by using factorized kernels, which incorporate local and temporal structure in the embedding. We first test our approach on a planar navigation task. As a baseline, we compare to MPPI, a common sampling-based MPC algorithm. Here, SVMPC can be seen as a distribution over MPPI controllers. Each color represents a different distribution of rollout trajectories produced by a single particle. As can be seen, this multimodal representation allowed by SVMPC allows it to capture narrow passages and quickly get to the goal. Next, we make a similar comparison on a high-dimensional reaching task, performing joint velocity control on a 7-degree of freedom manipulator. The grasp point of the end effector, indicated by the green dot, must reach the red target while avoiding obstacles. As can be seen, the unimodal distribution converges to a poor local optimum, and the robot quickly gets stuck between two obstacles. The multimodal distributions of SVMPC can resolve multiple local optima simultaneously, allowing the robot to find a low-cost trajectory around the obstacles and reach the goal. Lastly, we briefly demonstrate early results of SVMPC on 2D trajectory optimization tasks, assuming a fully differentiable cost function. We optimize directly over sequences of 2D velocities where each trajectory results from a single particle. Here, the shape of the resulting particle distribution can be controlled by the parameters of the chosen kernel, such as the RBF bandwidth. Thank you for watching.